I just wanted to have a video here on some of the graphical aspects of one-to-one functions and their inverses. Okay, so here I am on Desmos, and I'm going to do a little graphing here. I've got some functions along the side here and some points, and the first thing I'm going to do here is go ahead and have one of the simplest functions you can imagine here. I'm going to have the function y equals f of x is actually just x. So f of x is x. Some people would call that the identity function. Okay, so what goes into that function pops right out again. Okay, so this would include points like 0, 0, 1, 1, you know, 2, 2, 1.69, 1.69, and so forth. Here, if we were to imagine it as a set of ordered pairs. Okay, so the graph of this is y equals x. We all know that's a line through the origin with slope 1. And we're going to see this is important actually for one-to-one functions. Now, here's our question here. Is this a one-to-one function? Well, if you remember in a previous video, we mentioned that a function graphically, a real function, that is a function with a real domain and a real range, is going to be one-to-one if and only if it passes both the vertical and horizontal line tests. That means what? Every vertical line intersects the graph at most one point, and every horizontal line intersects the graph at most one point. Okay? That's what will make the function one-to-one. It simply means corresponding to every x value in the domain, there's exactly one value with the range and vice versa. Okay, let's look at this very simple function, y equals x. Okay, so the function is x. X goes in, x pops out. And there its graph, the graph of it, that line. Does that line pass the vertical line test and the horizontal line test? Well, I think we can see that indeed it does. Every vertical line intersects at most one point. Every horizontal line does so also. So in fact, the simplest function here, just plain old x, f of x equals x, is a one-to-one function. Okay? Now I'm going to refer to that again later because I'm going to show you that's actually important in dealing with inverses of one-to-one functions. But let's take it off right now. Let's go over here. Let's go to this function. Okay? The quintessential parabola, y equals x squared. Okay? Is this a one-to-one function? And the answer is, well, it's a function, but it's not one-to-one. It's a function because you can see here that it does pass the vertical line test. Every vertical line intersects that parabola at just one point, or at most one point. Actually, it's exactly one point because the domain is all real numbers. But so one value of x goes in, one value pops out. It's a function. Is it one-to-one? And the answer is clearly no here. You could see, for example, there are, in fact, infinitely many horizontal lines. For example, the horizontal line x equals 2 intersects the graph at what? Two different points here, right? All right. All right, let's better, how about the horizontal line? Y equals 1, I'm sorry. Y equals 1, it intersects at two different points. Do you see right here, if I can get this right? It intersects at what? When x is negative 1, y is 1. And what? When x is 1, y is also equal to 1, right? Both those numbers have a square 1. So the function f of x equals x squared is not one-to-one. It is not one-to-one. It is not true that corresponding to every element of the domain, there's precisely one element of the range here. So that's not a one-to-one function. Okay, let's take that off here. By the way, could you extend that? What about x to the fourth or x to the sixth? Okay, keep that in mind here. Well, let's do another odd power one. That's actually an odd power, isn't it? X to the first power. Let's look at this one. Do you know the graph of our fundamental cubic here? Y equals x cubed. Okay, nice power function here. This is what it looks like. If you guys think about it, it actually has origin symmetry. Okay, we'll talk about that later here. what about this thing? Is this a one-to-one function? Is it true that corresponding to every value in the domain, there's exactly one value of the range? And the answer is yes. And we can tell that by what? The fact that it passes both the vertical and horizontal line tests, right? Okay. Yeah, every horizontal line intersects the graph at most one point. So does every vertical line. It's a one-to-one function. Okay, so y equals x cubed. It is a one-to-one function. Now, what if I was to do this and go up here to y to the fifth power? Now, in the next chapter, we're going to go ahead and we'll be looking at some different power functions and polynomials, but let's just try this. It looks rather similar here, okay? All right. How about this, though, if I go to the fourth power? It looks more like what? The parabola, doesn't it? Okay. The rule's going to be here for these power functions that what? If the exponent, the power, is odd, it's going to be one-to-one. But if the power is even, then it's not going to be one-to-one. Okay? All right? Let's go ahead and talk about this. I want to come over here. I'm going to put this line back up here. Okay? Y equals x. I said it was going to be important when we talk about inverses of one-to-one functions. Okay? Here's just a quick question here. You remember in the previous video that I said you could imagine the inverse of a relation, okay, by what? By taking all the ordered pairs and just changing the order of the elements, okay? So here, imagine that I've got what? Negative 2, 3 as being an ordered pair in my relation, okay? If I was to switch those two, okay, transpose them, or whatever fancy language you like, then I would have what? 3, negative 2. Okay? Now let's label that one. Okay? So you see these two? We've done the switch, the transposing of these two, right? Okay? Now, do you see a relationship between these two relative to this line? Okay? Alrighty? Think about that for a second. Okay, I'll give you another one here. Suppose I have 1, 5 and 5, 1. Let's label those as well. Okay. Do you see a relationship between these points and that line? Okay. Alrighty. I'll explain what the relationship is. If you imagine the green line here, the line y equals x, acting as a reflector, a mirror here, what happens is, if I've got a particular value x comma y here, and I want to reflect it across that line y equals x, I actually get y comma x. In other words, when I switch the ordered pair here, what I get is what? The point, the reflected point on the other side of this line, y equals x. Okay? So y equals x, when it acts as a reflector, actually does what? It actually switches the ordered pairs. Okay? So let's say I had this as a function here. Do you see what I'm doing here? Let's say I had these two ordered pairs up here at the top, negative 2, 3, and 1, 5, as ordered pairs in my function. Okay? That would pass the vertical and horizontal line test, wouldn't it? Every vertical line intersects the graph at most one point, so also for every horizontal line. Okay, so this is my function here. Function just consists of 2 points. If I actually take its inverse function, right, which would exist here, it's actually, you see the reflection across the line y equals x here. Okay, the reflection across the line equals x gives you the inverse function. In other words, just the switching of the ordered pairs. Remember, that's all the inverse of a function or relation is. Okay, let's try that over here. Let me get rid of these now. I'll take off the labels. And I'm going to show you what happens here. We talked a little bit in a previous video about finding the inverse of a function given a formula. And if you remember, we had y equals x cubed, had an inverse being what? The cube root. Now what I want to do is graph these two together. Okay, here's the idea again. Okay, I've got my line y equals x. Here's my original function, the cubing function that's in blue. If I reflect that blue curve across that line y equals x, I get its inverse function, right? Okay, since that curve was 1 to 1, so is also the reflected curve here, as it turns out, and that's the inverse. So you see y equals the cube root and y equals x cubed. The graphs are reflections of each other across the line y equals x, and that always holds. Okay, if I have any function, one-to-one function, or even a relation, and I reflect it across the line y equals x, what I'm essentially doing is just switching all the ordered pairs making up the relation or the function, one-to-one function, okay? Alrighty, so this is just an illustration of this. So you can see why y equals x is actually fundamentally important with regard to one-to-one functions and inverses. Okay, all right, so just this short video.